All right, so thanks. Hope everyone had a good lunch, and we'll get started with the first lecture of our last lecture series with Steve.
Yes, okay, good afternoon, everyone. So I'll start by thanking the organizers. It's a real pleasure to be here, to be part of this nice summer school. I have some lecture notes online. Start by saying this. So I think you can click on the website of the summer school and find them, or you can just find my website. I have two hard copies, one on American paper, thanks to Allison, and one I brought from Leipzig. So I'll just pass this around in case you want to have a look. Okay, so you'll find more details of everything in there, so you don't need to write everything down that I read on the blackboard. I'm very happy with comments though, so if you find typos or any issues, let me know. Okay, the title is Positive Geometry of Polytopes and Polypoles, and I'll just slowly start by saying what the first two words mean. Okay, so positive geometry has been mentioned before in the other lectures. This is a emerging new field of applied mathematics, studying the geometry. This is broadly interpreted like real, complex, and tropical algebraic geometry, and combinatorics. Of physical observables. And here, the main examples I have in mind are scattering amplitudes in particle physics, and cosmological correlators. Okay, so that's my best shot at a one-sentence definition of what positive geometry means. The motivation so comes from theoretical physics. One of the main breakthroughs has been the discovery of something called the amplituhedron, which Mark is taking us through in his lectures. So this is a geometric object. It's a semi-algebraic subset of a Grassmannian, the real points of a Grassmannian, whose geometry sort of tells you how to write down an amplitude in some particular theory called n=4 superangles. Okay, now, this was 2014. It was discovered by Nima, who lectured yesterday, and Jaroslav Tymka. But after that, there came many other examples. So other examples of geometric objects underlying some of these physical observables. I'll mention a few. There's something called the correlahedron. So this captures stress energy correlators in n=4 super-Yang-Mills. There's ABHY associahedra. I will explain a little bit what these are in the next lecture. There's something called surfacehedra. So I'm just giving you these names in case you want to Google. And on the cosmology side, there are cosmological polytopes and cosmohedra. And so from what I understand, these surfacehedra are a bit to these ABHY associahedra what cosmohedra are to cosmological polytopes. If you want to pass from tree level bi-adjoint scalar to all loop level, then you need to consider surfacehedra. And okay, the analogous statement is true for cosmological polytopes versus cosmohedra. Okay. Good. So all of these objects, they share some common features because of underlying physical principles. But these principles, I think, or at least among them, are locality and unitarity. And these common features, they sort of express the need for a unifying framework, a unifying mathematical framework which allows us to study these objects systematically. Okay. That's my one Blackboard motivation of why we're doing the things that will come. That will come in my lectures. So the plan, as you know, there's 3 parts. In my first lecture today, I'll just talk about definitions and examples. And then the rest of the title will come in lectures 2 and 3. So 2 is polytopes. And 3 is something called polypoles. So that's POLY, POLS. And I'll tell you what those are tomorrow. Okay. Questions, remarks already? No, then we start with section 1. Okay. Okay. So definitions and examples. My plan is to explain 2 definitions. So the truth is, as I said, this field is still like in its early stages. It's a bit in its infancy. And I think there are several candidates for the definition of what a positive geometry should be. I will start with a first definition given in 2017 by Nima Arkhani-Hamid, Bai and Lam. And this will take me a while to get to that definition. I'll need to introduce some concepts, and then by the end, I will explain a more recent candidate inspired by a paper of Brown and Dupont. See if I have more. Okay. So X throughout the lecture is an irreducible, complex projective variety. Of dimension D. I know it's a diverse audience, so if any of these words don't mean anything to you, please just interrupt me. Okay, so this is an algebraic set in the projective space. It means it's defined by polynomial equations, and it's irreducible in the sense that you cannot write it as a non-trivial union of several such things. Okay, X non-negative is going to be a closed semi-algebraic subset of the real points of X. And I want this to have dimension D as well. But there's an assumption here. So I'm assuming that my irreducible complex variety X has sufficiently many real points so that I can actually find a semi-algebraic subset of dimension D in there. Okay. Another thing I'll require is that X is sufficiently nice in the following sense. If I take the interior of X non-negative, and then I take the closure, so both interior and closure here are with respect to the analytic topology on the real points of X. So yes?
Probably really stupid, but how do you define the dimension of a semi-algebraic set?
So you can look at it, let's see. So this might have several components. Let's say this is connected. Let's say you look at the individual connected components, and for each connected component, you take a point in the relative interior and you take the dimension of a ball that fits around it. It's what you intuitively think it is. Other questions? And then if there are several components, then it's not equidimensional maybe, but let's say I want all components to have the maximal dimension. Okay. Okay, so this, I'm going to add to this that the interior of X non-negative is orientable. An oriented real manifold. Okay. So here it might be useful to give you an example of why or what this assumption means. So you can imagine the graph of a polynomial in one variable. Polynomial f. Now you can look at all the points x on which this polynomial is non-negative. That will give you the following semi-algebraic set. It will give you the union of this point right here and this interval right here. Okay. Now if you take the interior, this point drops out, right? And you close it up, you're only left with this interval. So this is not allowed. I don't want subpoints in there. Okay. Right, and so oriented real manifold means we don't want things like Möbius strips. Okay.
You want to make any smoothness assumptions?
Sorry?
Are you making any smoothness assumptions?
Not so far. No, not yet. Okay. Y is going to be the Zariski closure of the boundary of X non-negative. So this partial symbol takes the boundary. So that means X non-negative minus its interior. I'm also going to give you some examples in a second. Okay, so Zariski closure means closure in the algebraic sense. So I take the smallest algebraic subvariety of X that contains the Euclidean boundary of X non-negative. Okay. So this is called algebraic boundary. And I will write y1 union ... yr for the irreducible decomposition of this algebraic boundary. Okay. So each of these yi is an irreducible divisor, a prime divisor on X. It's codimension 1 subright. Okay. Do some examples. Okay. Okay, so here in the first example, X is one-dimensional, so D is 1. X is going to be the curve in the plane given by this equation. So it's affine chart where x0 is non-zero. This is the circle. I'm drawing the real points of X in white. X non-negative is going to be this curved segment. It's going to be the intersection of my circle with R2 plus. The boundary Y consists of these two blue dots. So this is y1 and y2. So R is 2, D is 1, and green is x not negative. Okay. Go one dimension up. And I'm going to take a conic in the plane together with the coordinate axes. I'm going to select this shape. This is x non-negative. The Euclidean boundary of x non-negative consists of these three curved segments. Okay. But the smallest algebraic curve containing the bold blue curve is the union of all these three. Is the two lines union the circle. Y1, Y3. So I should have said X. X is the projective plane, P2, the complex projective plane, P2. So negative is the green region, and Y is a union of three components. Okay, so of course I'm giving these examples because these shapes, they will be examples of positive geometries. And this sort of tells you that instead of just allowing line segments or things that look like polygons or polytopes, we also want to allow more curvy shapes. Okay. And one of the main features of positive geometries will be the existence of a canonical form whose residues on the boundary are also canonical forms of positive geometry. So the first definition I'm going to give is recursive. I want that these boundary components of x non-negatives will also turn out to be positive geometries of one dimension lower. Okay. So to formalize this, I need a bit more notation. So for each boundary component, so for each component yi of the algebraic boundary, I define the non-negative part as the closure of the interior of x non-negative with yi. Okay, so here I take the green shape, I intersect it with the blue curve, with one component of these blue curves, and I get, for instance, this line segment as the positive part of y1. Okay. All right. So I was talking about taking residues of differential forms. Let me first tell you the definition of the differential forms that I'll be considering. So here's the smoothness assumption for this definition. So if X is a smooth variety of dimension D, they'll say a rational D form omega on X is a differential D form such that on each chart you can express omega as a function times dx1 dot dx3. And here h, you pull back h to x, and this is a rational function. This is a rational, well, restriction of a rational function. The restriction to U of a rational function of X. Okay. This is the definition of a rational D form. Very concretely, you do this for X's projective space. Will be largely enough for these lectures. In this case, you can just write an expression for omega on an affine chart, which is, oh, I wrote G over F. Let me stick to that. Sorry. Where here F and G are polynomials. I can assume they're co-prime and the denominator is not zero. Okay. Okay, so this omega is said to have a pole of order k along a prime divisor that's locally driven by some equation f0. If you can write f, or if you can write f as f0 to the k times f1, and k is the largest integer for which you can do this. Anything unclear about this? Okay. So this is what you do for, these are the forms we consider on smooth varieties. So in general, so for general X, meaning irreducible of dimension D, I'll say rational D form on X to mean irrational D form on the smooth points.
The X is the coordinates on PD, so it's
So-
divided by the first coordinate.
No, so here I'm using x1 dot 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 xd as coordinates on an affine chart of PD. So here you can think of V equal to CD and U as a x0 non-equal, yeah. Okay. Yes, so what I'm going to need in the definition of positive geometry is I'm going to have to take residues of these forms, right? Of these forms, so I need to tell you what that means. So if omega is a rational D form on X with a pole of order at most 1, We also say that omega has at most a simple pole along some prime divisor. I'm going to assume that this prime divisor does not belong to the singular locus of X. And locally at a smooth point, of yi that is not on the singular locus of X, we can write omega as follows. You write omega as some d minus one form, wedge df over f, plus another d form eta prime that has no poles. So eta and eta prime, they have no poles along f. So f is a defining equation of yi. So I'll write fi. So yi locally given by fi equals 0. Okay. You first write, to take a residue of omega, you first write omega like this. You sort of split off the pole along fi equals 0, and then the residue along yi of omega is the restriction of this d minus 1 form eta to the d minus 1 dimensional boundary component yi. We'll do examples. Okay, yes. What do we know about eta prime? In many cases, in all our examples, you will not need eta prime. Okay, so let's do an example. And here, notice I need to, in order to be able to do this, I need to find a smooth point on X to have local coordinates in the first place. And in order to have this local defining equation that vanishes to order 1 along yi, I need to be also locally at a smooth point of yi. That's why we have these assumptions. And these assumptions are quite restricted. I'll come back to that. Examples. Let's take the residue of the following rational form on P2. To do some audience participation. Okay.
Right, x over x with y over y, and then switch the ordering.
Okay, so Mita is suggesting we first write this as, so you say that again?
You can do dx over x with
Yes.
dy over y. And then that's negative dy over y. X. And then I think that satisfies our conditions.
Exactly. Okay, so
Yeah.
this is eta. Okay. So this is minus dy over y. And we're now using y as a coordinate on the y-axis. Okay. Similarly, take the residue along the x-axis instead. you'll find dx over x using the same algorithm. Okay. Now notice, so geometrically, we've been looking at this, configuration of lines in the plane. We take the residue along x equals 0, we see minus dy over y. Take the residue along y equals 0, we see dx over x. Now these lines intersect in this point. And what we could do is we could take the residue at this point of both these resulting forms, right? I'm making this point because we'll need it later. If I take the residue at 0 of this form, it's going to be, maybe I'll make use of it. Yes. Thanks, Veronica. This is -1. So this is going to residue at 0. Gives you -1, and the residue at 0 here gives you 1. Okay, so you can take iterated residues to get to higher codimension boundary components, but you might get the same result up to psi. Okay, this will come back later. Okay, then I'm ready to state the definition, first definition. So this is, as I said, in a paper by Arkani Hamid, by and Lam, 2017. Okay, so the positive geometry is going to be a tuple. So I'm going to say that the tuple x comma x non-negative is a positive geometry if there exists a unique non-zero rational form or omega of x non-zero. There's a rational E-form on X called canonical form. Satisfying the following recursive axioms. Okay. As I said, it's a recursive definition. The end of the recursion is when the dimension is 0. So if D is 0, then all you need to check is that X is a point. Because the only irreducible 0-dimensional variety is a point, and its canonical form is plus or minus 1, where the sign is the orientation. Okay, so 0-dimensional positive geometries are easy. They're just points with canonical form plus or minus 1. Okay. I'll need a bit more space for grid consider. Okay, if D is greater than 0, then this form, so the canonical form, is required to have simple poles along the irreducible components of the algebraic boundary. And here I'm going to require that R is greater than 0, which maybe is implicit because I started indexing at 1. And because I only told you how to take residues under this assumption, I will assume that yi is not contained in the singular locus of x. Okay. Moreover, I do not want it to have poles elsewhere. Okay, and it has no poles. No other poles. On the smooth points of x where it's defined. Okay, so this in physics I think is called a locality. Somebody can correct me if that's not true. Moreover, and this will be unitarity, if you look at the tuples yi non-negative, these are d-1 dimensional positive geometries. Whose canonical form is only allowed to be one thing. You take a residue along yi of omega x. Okay. For quite a mouthful. But this is the definition first stated in this paper, which I think is a first attempt to developing this mathematical framework of positive geometry. Yes.
Do you need the word unique?
In this definition, I certainly don't. I think you stressed this morning that you like it.
Like, because we come from the other point of view, but I just wonder if you know an example of a space that satisfies all these axioms, except there are two different possible canonical forms.
Yes, so if any space with holomorphic forms will do. Right? So if you take an elliptic curves in the plane, then you can add any holomorphic form to your candidate, and it will either still satisfy the axioms or it to begin. Yeah.
Where does the orientation yi greater than 0?
Oh, good point. I forgot to say that. So that needs to be induced by the orientation of x greater than 0. I actually forgot to add that to my drawing. Thank you for that question. So we were looking at this this configuration. And I didn't tell you in these pictures which orientation I chose. So let's say I choose this orientation for x non-negative, x positive. Then the orientation of this curve segment is the induced orientation. More questions? Yeah, very good question. Okay, now there's a bunch of examples coming. So this is, okay, maybe a criticism or disadvantage of this definition is that it's really quite technical to state, but then at least it's quite concrete and you can verify that positive geometries exist by doing some interesting examples. Okay, so let's start in dimension 1. So dimension 0 is sort of boring. Only positive geometries are points and all canonical forms are plus minus 1. In the projective line, I can consider a line segment, AB. So this sits in R. Inside RP1. And I'm claiming, so the orientation, I'm assuming A is smaller than B, and I'll orient it from left to right on the real line. The canonical form of this positive geometry, I claim, in a local coordinate x on R is this. Okay, so let's check this claim, verify this claim. First of all, there are simple poles along Y. I hope you agree. So green line segment Y is the union of the points A and B. Are simple poles at x equals A, x equals B. Okay. Good. Now, turns out there are no other poles on the projective line, right? In order to verify that, you would have to go look on the other chart, see that there's nothing at infinity, but that is in fact true. Okay, and this form also has no zeros on the projective line. Oh, super. Okay, so that means, okay, if there were another form with this property, with having no zeros and only two simple poles at A and at B, then the quotient of omega in that other form would be a holomorphic form on P1. Right? So that quotient would have to be a constant. So the only candidate canonical forms, if this is in fact a canonical form, then the only candidates would be multiples of omega. Is that clear? So this is typically how you show uniqueness. Like if this satisfies the residue condition, this is the only candidate. Okay. Because if I were to multiply this with a constant that is not one, I will mess up the residues. In the end, when I go to the boundary, it needs to be plus this. Okay, so all we need to check is that the residue at A and at B is indeed plus minus 1. So the residue at x equal A. Okay, I'll spell it out one more time. So this is the residue at x equals A of B minus A over B minus x. Bx minus A over x minus A, which is B minus A over x minus B minus x. At x equals A, which is 1. Okay, and I'll leave the residue at x equals B2. Okay. So, and then we're done, right? Because there's only one step in the recursion, we were already in dimension 1. A similar example, it's in fact the same example, but let's do it anyway. If you, that x is C1 again, and x non-negative is the closure of R plus. This is often written as P1 non-negative, the non-negative part, P1 or okay, this will have canonical form in these local coordinates on R. This will have canonical form dx over x. Okay, and this is also something, if you're not yet familiar with it, you should check it. Now, if you look at what this form does on the other chart, you'll see that it has another pole sitting at infinity, which is the other boundary point. So essentially, this is the same example, except A sits at 0 and B sits at infinity. Okay, this more generally, a d-dimensional projective space, you take R plus to the d, close it up. This is the non-negative points ED, and the canonical form will be 1 over x1 dot 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 xt, dx1 dot 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 dxt. Okay, so positive orthants are positive geometries, which I think one would expect. Positive orthants are like simplices, so we consider a triangle in the plane. With x non-negative, y non-negative. 1 minus x minus y non-negative. It's this picture. So there are 3 boundaries to check. I'm going to give you a candidate canonical form. It is this one. Okay. All right. So again, the strategy for showing uniqueness would be the same. So I need a form that only has poles along the 3 blue lines. Remember to check at infinity, right? But this pole only has forms along these 3 blue lines. And then it cannot have any zeros because the canonical divisor E2 is 3h, right? So that if there is another form with no zeros and 3 simple poles along these lines, it's a multiple of omega. So if this has residues plus minus 1 in the corners, then they're done. Okay. Let's see. Okay. In the interest of time, I'm going to skip the next. There's many examples in the notes. Okay, so you can have a look at other examples there. In particular, the one, let me talk about the one where we turn this third line into tonic. Then I'm going to spend a couple minutes talking about the other definition. So in this example, what a bit misleading in these previous examples as well, I now leave you to do exercises and you have to come up with a candidate for a canonical form. You just put 1 over the defining equations in the of the boundary components. And so this example is to show you that that's not, in generally, that you don't get away with that. So here the right form adds an interesting numerator. So certainly in the denominator, we will find the components of the boundary. But in the numerator, there appears this linear thing. And you really need it for everything to work out. So you can test this in the exercises. And okay, so you see a polynomial, we are trained to ask what's its 0 set. So if we draw the 0 set of that polynomial in this picture, then you'll find that it's the unique line connecting these 2 red points. And that's of course no coincidence, and we'll talk more about that in the near future. Okay. Questions while I erase? Good. Okay, so now I'm going to give you another possible definition for which I need to take responsibility. So this is inspired by a recent paper by Brown and Dupont, but I'm not putting words in their mouth. I'm just, they don't give an explicit candidate for a definition based on their work. But I emailed this to them and they didn't disagree. So okay, so X, this needs fewer ingredients, so I won't go over time. X is an irreducible complex projective variety as before. mention B. Y this time needs to contain the singular points of X. So this closed subvariety doesn't need to be a divisor. Closed subvariety such that X minus Y is smooth. So Y contains the singular points. Okay, so a relative B chain. Oh, sorry, the relative D cycle. My notes. A relative D cycle of the pair X comma Y is a D chain on X whose boundary is contained in Y. If D chain on X, the boundary contains Y. And I'm going to write sigma for the homology class of such a D cycle. This is relative homology for the pair X comma Y. Here's a definition into Brown and Dupont. So they say that the pair X comma Y has genus 0. If the mixed Hodge numbers of this relative homology group are 0 for positive P. Okay, so I need to give you fewer ingredients, but fewer people know what the ingredients are. So, okay. And they observed that in their paper, they observed that if X comma Y has genus 0, then there is a canonical map. Non-equal. There's a canonical map which takes a homology class of a relative D cycle and it associates to it a logarithmic differential form on X minus Y. Let me call this, again, even though I should take responsibility, let me call this the BD definition. A positive geometry could be a relative homology class of the genus 0 pair. And in that case, the canonical form okay, so you take a homology class sigma and the relative homology of a genus 0 pair X comma Y. And then you send it through this map to find your canonical form. And in fact, so in their paper, Brown and Dupont, they provide many tools to check whether your pair X, Y is genus 0 without you having to know about mixed Hodge theory. Right, so, and they also show that if you have a genus 0 pair, then the form that you get from this map under appropriate assumptions actually satisfies all the recursive properties that are required by the previous definition. So in my view, the precise relation between these two definitions is not super clear. First of all, for instance, this definition doesn't talk about real points at all, which is a criticism for this. Positive geometry maybe should have something to do with the real numbers. Another, let's see. So this also doesn't require the form to be non-zero, which is, I know something that Clément feels strongly about, and I think I agree. So maybe you want to have this property that if you make a union of two positive geometries, you just add the canonical forms, and then it's strange to exclude 0. Okay, so again, it's a very much in its infancy, so we're still looking for the correct definition. It is not guaranteed. If you have a genus 0 pair, then that property is not recursive. So if you go to a boundary component of a genus 0 pair, you might lose the genus 0 property, so the full recursion might fail. And this might be not desirable in the physics application. Okay, so plenty of stuff to talk about. So I think what many people do agree about is that polytopes should be positive geometries. And I will try to convince you that that is true according to both definitions in the next lecture.